You're at a cafe with a wobbly table. You slide a napkin under one leg, but then another leg pops up. Fixing this isn't about one leg, it's about how all four legs change together. We'll crack this puzzle. We just saw a wobbly table. To fix it, we need to know how much the floor height changes when we move. That's the Jacobian. The Hessian tells us how that change itself bends. Think of a simple slope on a graph. The Jacobian is that idea, but for many inputs and outputs. It's a matrix, a grid of numbers, where each number is one tiny slope. The name honors mathematician Carl Jacobi. If the Jacobian is your speed, the Hessian is your acceleration. It captures the curve, or twist, of the landscape. It's named for Otto Hesse and is a square matrix of. We just defined the Jacobian and Hessian. Now, let's see why they matter. Imagine a wobbly table, each leg's length is a variable, and the wobble is an error we want to eliminate. The Jacobian acts like a sensitivity map. It tells you precisely how much the wobble changes when you adjust a single leg, so you can calculate the exact shim thickness to stop the rock in one go. We just saw why these matrices matter. Now, let's build them from scratch. Imagine a hiker on a warm hillside. She feels the slope under her feet, but the steepness changes depending on which way she faces. If she steps straight uphill, the temperature drops fast. If she steps sideways along the hill, it barely changes. The slope she feels is a rate of change, and it depends on her direction. A single number, like the slope is 10, only works for one chosen path. To understand change in every possible direction at once, we need a new kind of tool. That tool starts with the J. We just felt the slope on a simple line. Now, instead of one input, we use two, like coordinates on a map. The output becomes a height, creating a surface we can explore. Think of the xy plane as the ground. For every point you pick, the function gives an elevation, turning the flat input space into a rolling 3D landscape. Pick any spot on this landscape. To understand its shape, we need to measure steepness. But unlike a simple line, the slope here changes depending on which way you turn. We just stood on a 3D landscape. To measure its steepness, we slice it along a pure x direction, holding y constant. This reveals a simple 2D curve whose slope is the partial derivative. On this x slice, we draw a tangent line at our point. Its slope, rise over run, is the partial derivative with respect to x, written with a curly d, f x. It measures pure x steepness. Now we hold x constant and slice along y. The tangent line on this new curve gives us fy, the steepness in the pure y direction. Together, these two numbers capture the full slope. We just sliced the hill to find two separate slopes. But a hiker needs one single best direction to climb. We combine the partial derivatives into a single vector, the gradient. This combined arrow points exactly where the hill rises fastest, the direction of steepest ascent. Its length tells you how steep that climb is. It always points straight across the flat contour lines. We just found the steepest path on a landscape. Now shift perspective, instead of one output height, imagine the function moves each point to a new location, like stretching a rubber sheet. Picture a regular grid of points in the input. After the transformation, straight lines bend into curves. The Jacobian, which we met earlier, now measures how much a tiny square locally stretches and rotates. We just saw a transformation warp a whole grid. Now, zoom in on one tiny square. As we get infinitely close, those curved lines look perfectly straight. Picture a microscopic square in the input space. After the transformation, it's no longer a square, it's a parallelogram, with opposite sides parallel and equal. That local stretching and shearing is exactly what the Jacobian matrix captures. It's the simple linear recipe that mimics the transformation right at that spot. We just zoomed in and found a flat, linear map. But a transformation has multiple outputs, like u and v. Each can change with respect to x and y, so we need a table to capture every slope at once. We stack these rates into a matrix. The first column holds all partials with respect to x, how the whole output shifts when you nudge x. The second column does the same for y. Each row tracks a single output component, u or v. This table is the Jacobian matrix. Multiply it by a tiny input step, and you get the output change, the same linear map we saw when zooming in. It captures all the local stretching and shearing at that exact point. We just captured local stretching with the Jacobian matrix. Its two columns form a tiny parallelogram in the output. The area of that shape is the determinant, a single number that tells us how much a small patch of input space expands or shrinks. If the determinant is negative, the patch hasn't vanished, it's just flipped over, like turning a page. The absolute value still gives the area scale factor, but the minus sign tells us the transformation reversed the order of the edges. For a 2x2 Jacobian with entries a, b, c, d, the determinant is simply add minus bc. That one number captures both the area scale and whether the local patch got mirrored, all derived from how the columns span the tiny output parallelogram. We just measured how area distorts. Now let's return to our landscape. A first derivative gives the slope, the tilt of the ground under your feet. But a hill can tilt the same amount yet feel completely different. What we need next is curvature, how the slope itself is changing. Imagine standing in a bowl. As you walk right, the ground tilts upward more and more, the slope increases. That's positive curvature. On a dome, walking right makes the slope tip downward, negative curvature. The second derivative captures this with its sign. Back on our 3D landscape, we can slice the hill along pure x or pure y, taking the derivative twice along the same slice. Written squared f(x squared) tells us if that slice is bowl-shaped or dome-shaped. Do the same for y, and we have curvature in both compass directions. We just measured curvature along each axis. But what if the x-slope itself changes as we step in the y direction? That's a mixed derivative, the twist of the surface. Imagine slicing the surface at y equals 0 to get the x-slope, then at y equals 1. If those tangent lines have different steepness, the surface is twisting. On a saddle, the x-slope actually reverses direction as you move in y. Here's a beautiful fact: for any smooth surface, the twist you get by differentiating first x then y is exactly the same as first y then x. The mixed partials are equal, the surface twists symmetrically. We just saw the twist, a mixed partial derivative. Now, let's collect every second derivative at a point into one organized grid. This grid is the Hessian matrix. Place the pure x curvature top left, the twist top right. By Clairaut's theorem, the twist is symmetric, so bottom left is the same. Bottom right is the pure y curvature. This 2x2 matrix is the Hessian, denoted H. Together, these numbers capture every way the surface can bend or twist at that point. The Hessian defines the perfect quadratic bowl, curving up, down, or twisting, that hugs the surface most closely right there. We just built the Hessian, a matrix of all second derivatives. Now, at a point where the gradient is 0, the ground is flat. But is it a peak, a pit, or a mountain pass? The Hessian holds the answer. Imagine a simple bowl, like f equals x squared plus y squared. At the bottom, every direction you walk curves upward. The Hessian captures this, its eigenvalues, which measure pure curvatures, are all positive. This is a minimum. Flip the bowl upside down, all curvatures are negative, so it's a maximum. But if one direction curves up and another curves down, you get a saddle, a mountain pass. The determinant of the Hessian tells us, positive means both curvatures agree, negative means they disagree. We just used the Hessian to find peaks and pits. Now, let's see the Jacobian in action. Imagine a robot arm. Turning its joints changes where the hand ends up. The Jacobian also rules computer graphics. When wrapping a flat texture onto a 3D model, the Jacobian of the mapping tells you exactly how much the image is being stretched or squashed at each point. Artists use this to minimize distortion. Switching to the Hessian, in machine learning, we hunt for the lowest error. A zero gradient tells us we found a flat spot, but is it a pit or a pass? The Hessian's eigenvalues give the final answer. All positive means we're truly at the bottom of a bowl. We just saw these tools powering robots and AI. Now let's connect the dots. It all started with a single slope. Then, for a landscape with two inputs, that slope became a gradient, a vector pointing straight up the steepest hill. Next, we viewed a function as a transformation, squishing and stretching input space. Zooming in, it looked linear. The Jacobian matrix captured that local stretching, and its determinant measured how much a tiny area grew or shrank. But stretching is only half the story. Second derivatives measure bending, how a surface curves. The Hessian matrix packages all that curvature together, telling us if we're at a bowl-shaped pit, a dome-shaped peak, or a twisted saddle pass. Let's pay off our opening puzzle. Imagine the cafe floor as a bumpy surface where height is a function of position. The tables for legs land at 4 different points on this surface. A wobble means those 4 points don't all lie on one flat plane. Now, instead of shoving napkins, we rotate the table. As it turns, all 4 leg heights change simultaneously, tracing curves on the surface. We're hunting for the rotation angle where the height difference between legs vanishes. That's the Jacobian in action, linking all changes together. For our bumpy floor, the magic happens near a 45-degree rotation. At that angle, the surface's local slope under each leg averages out and the table sits flat. The gradient, our Jacobian for height, is nearly 0 across all 4 points, meaning no single leg pushes up or dips down. We've seen these tools in action. The single biggest mistake is memorizing the calculation without the story. The Jacobian measures local stretching, the Hessian captures the bowl-like curvature at a point. Link the letters to a mental image. J is for jelly, the Jacobian shows how a tiny square of jelly gets stretched and sheared. H is for hill, the Hessian tells you if you're standing in a bowl, on a dome, or at a saddle. Test your understanding on the simplest 3D bowl. Find the gradient and Hessian at the point 1, 1. The Hessian should be a simple diagonal matrix, and its unchanging positive values confirm you're in a perfect, round